All right. So today we're going to look at electron configurations. We're going to get a little bit into light and electromagnetic radiation, okay? But big focus on electrons here. Electrons are key to our understanding of chemistry, okay? So buckle up. Here we go. A couple things we want to make sure we do. We want to make sure that you have a pretty decent understanding of the wave model, the quantum model from our presentation on atomic history. We're going to look at that today. We want to compare and contrast the Bohr model with the quantum model, okay? Because we're going to see those two things kind of interplay a lot. The quantum model is the accurate representation of reality, but the Bohr model is really good for helping us to kind of visualize what's going on in our atom. We want to look at the Heisenberg uncertainty principle and the Schrodinger wave equation just a little bit. We're going to talk a little bit more about those atomic orbitals, but we're not going to go into great depth with that. We're going to learn about the four quantum numbers, how we identify specific electrons, and we're going to look at sublevels again. So I know we've seen sublevels before. So let's talk a little bit about those waves, okay? This idea that matter can be both a particle and a wave actually started with light. Light was predicted to be a particle and a wave. And Louis de Broglie suggested maybe electrons can also do that. They can behave as both a particle and a wave. And you can kind of think about that like it's, moving as a wave through space, okay, as a form of energy. And at certain points, it acts like a particle. So it is both a particle and a wave. And it doesn't have to be at just the top. It doesn't have to be just 1 second. It could be a bunch of seconds in a row. It's both a particle and a wave. Now, the thing about waves are they move in specific frequencies, okay? So they're going to have a certain amount of energy associated with them, and that frequency is their frequency. That's the identifying factor of a wave. So electron behavior follows the Schrodinger wave equation, which says E equals hv. And electrons within specific orbitals are related to those frequencies. So the more energy they have, the greater potential energy of the orbital. Now, Bohr called those energies orbits. And Bohr's model was great as long as you were talking about hydrogen. All right, all the math worked out for hydrogen because hydrogen has one electron. It also worked if you talked about one of the ions of hydrogen, which had one electron. But anytime we had more than one electron, it didn't work out. And so we kind of had to upgrade. We had to figure out a better answer. Now, Heisenberg, he points out that if you're going to have electrons acting as both particles and waves, and you want to know where they are, well, in order to do that, you have to bounce a photon off of it, right? Just like if I want to see something, I have to bounce a photon off of it. I have to do the exact same thing in order to figure out where an electron is. So the way that we see, all right, I have a tree here. Let me draw a tree. And here's my eye. It's a wonderful eye, right? Got some, there we go. Eyelashes and everything. So light from the sun gives off photons. They hit the tree. They bounce off the tree, and they go into my eye. And that's how I see things. If I want to see an electron, all right, I have my detector. This is our detector. I have some form of photon generator, so I'm just going to draw that as a light bulb, even though it's probably not a light bulb. All right, there we go. And then here's my little electron. So the photon comes in, hits the electron, bounce off to the detector. Here's the problem. When a photon hits the tree doesn't really move. All right, I can know that the tree is stationary or barely moving in the wind, and bouncing photons off of it, millions and millions and millions of photons, is not going to move that tree. An electron is really small. I bounce a photon off an electron, well, I'm going to change both its velocity and its position. So Heisenberg said, look, you can detect one or the other, but you can't detect both at the same time. And that's true of an electron or any other, simple particle. Same thing if I was trying to detect like a neutron or a proton, something like that. When I bounce that photon off of it, I'm going to change both of those values. I can only use the math to figure out one. The other one is too uncertain to tell. Now, when we're looking at the wave nature of electrons, right, so that's the particle nature, is Heisenberg. The wave nature is just, like we would be examining light. So you can diffract electrons, you can bend them. And whenever you put electrons through a small opening, or if it goes around the edge of an object, this is called diffraction. You're bending the paths of those electrons. And that's really interesting because this lets electrons do weird things. Like electrons can move through a solid wall. They're just on one side and then suddenly they're on the other. If you set up a slit experiments and you throw a bunch of electrons at a slit, well, they can actually seemingly go through both slits. So like if I set up my electron gun, right, and this is shooting electrons out as particles, and I have a screen set up, and the screen is solid except for two slits, I can actually start to build a pattern that looks like this. And it's not just the electron going through one slit or the other, it's actually its waveform, all right, going through. And what's happening is, if you project the waves over top of this, at some places the waves build on each other, and at some they counteract. And so that's called destructive interference. And these blank spots are places of destructive interference. You also have constructive interference where the troughs and the crests overlap, and they actually make bigger waves, all right, greater in amplitude. And so that is these colored in regions right here where you have constructive interference. And so electrons can do some pretty wild stuff, and you can look up some more information on the weird things that electrons do if you are interested in that. So the orbitals, right? So since we know that the electrons are moving not like particles around the sun, they're in fact moving as waves through space, they are confined to certain regions based on that destructive and constructive interference. They can't move through a place where they cancel each other out. And so the orbitals are these three-dimensional regions, all right? Let me move my face here. These orbitals are these three-dimensional regions around the nucleus that give you a statistically probable location for at least one electron. And we can look at those. So let's look at some of these interesting shapes. So first, we need to draw the periodic table. Oh, go back. So let me get my pen here. So let's draw the periodic table here. That was terrible. What the heck? There we go. All right. I know this is not to scale, but that's okay. So some things we already know about the periodic table, right? Number one, we have the S, the P, the D, and the F block, okay? And we also know that you can have 2 electrons max per orbital. So something that's kind of interesting here, the S orbital, it only has it only has 1 lobe. It can at most have 2 electrons in it. Now, if we look at the S block, there are only 2 columns of elements in it. And so like lithium, which is right here, and beryllium, well, the difference in electrons between lithium and beryllium is just 1. So lithium has 1 valence electron in the 2s orbital, and beryllium has 2 electrons in the 2s orbital. But now the s orbital is full, so I have to go to the p orbital, right? I go straight across to the p orbital. And actually, let me erase something here and redraw that. to make it a little bit more accurate. Because there is a space. There we go. All right, so as I go, once I fill up the s orbital, there's no d orbital just yet. I got to go straight to the p orbital. Now the p orbital has 6 columns of elements in it. So 1, 2, 3, 4, 5, 6. Well, I can put 2 electrons in an orbital. Each one of these is going to add 1 electron, so the p orbitals at most can hold 6 electrons. And if we look at this, well, I have the x orbital, the y orbital, and the z orbital. These are oriented in space around each other. So if I drew them all on the same axis, they would look like this. They kind of overlap each other. One centered on the z-axis, one on the x, and one on the y. Well, I can put 1, 2, 3, 4, 5, 6. I can put 6 electrons into those orbits. And that's, that makes sense. All right, so let's get rid of those. Let's look at the next one. All right, the d orbital. The d orbital can hold 10 electrons. All right, and there are 10 columns in the d block. 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you count the columns in a block, that tells you how many electrons can be housed there. So I can put 1 in the y, 1 in the x, 1 in the xy, because it's in between the x and the y. All right, 1 in the yz orbital, 2 in the yz orbital. I can put 1 in the xz orbital, and I can put 1 in the z2 orbital. And I like the z2 orbital. It kind of looks like a donut. So we have 2, 4, 6, 8, 10 electrons that can be housed there. So the orbitals are pretty cool. They, match the, there has to be an orbital for each of the electrons that is housed in that space, okay? So those are some of the shapes. Now, there are also F orbitals, and like I said, G and H orbitals. They're very complicated looking, but if you want to look them up and see a picture of them, you're more than welcome to. And see, we use the quantum numbers in order to describe those orbitals. So kind of think about the electrons as tenants, right? People who live in a house. And so we need to give each electron an address in order to describe where it lives in those orbitals. And so we do that with 4 quantum numbers. And one of the principles of these quantum numbers is no 2 electrons in the same atom can have the same set of 4 quantum numbers. 3 of them can match, but at least one of the 4 has to be different. So the quantum numbers start with the principal quantum number. It tells you the main energy level occupied by the electron. Now, you guys already know these. They're the numbers 1 through 7 that run down the left side of the periodic table. It'll tell you which row you're looking at. That's the main energy level occupied by the electrons in that row. The second is the angular momentum quantum number. We usually symbolize it with L, but it tells us the shape, S, P, D, or F. You already know those, right? We know the S block, the P block, the D block, the F block. The next 2 quantum numbers are the magnetic quantum number, which is symbolized by M, which tells us the orientation of an orbital around the nucleus. Now, in upper level chem, you might have to memorize these. In my class, you don't need to. I'm going to show you what they are. I'm going to show you kind of how they make sense, but I'm not going to make you identify the magnetic quantum number. The last value is the spin state, okay? It can only have 2 numbers. It can either be plus a half or it can be minus a half. And this indicates which way the electron is spinning in that orbital. Is it spinning up or is it spinning down? That'll be more important later on. So here's what we want to do with this. We want to be able to identify where things are living, or where the electrons are living around this atom. We want to use the off-ball principle, the Pauli exclusionary principle, and Hund's rule in order to identify correct electron configurations. That's what we call the address where an electron lives, and incorrect electron configurations. We also want to be able to use something called orbital notation, electron configuration notation, and sometimes noble gas notation, which is often called shorthand. So let's look at electron configuration, right? Just like your house has a physical address, Electrons have a physical address based on where they reside. The S, P, D, and F are kind of like neighborhoods, and the energy levels are like the street numbers. So let's see if we can put those together. On the left side of your periodic table, you'll notice there are these numbers. They go 1 to 7. That's the principal quantum number. Now, the D block, and this is important, is always one less than the S block. So if I'm reading left to right, the 4S elements, once I'm finished with the S block, this line, I go from 4S to 3D. The F block is always 2 less than the S block. So right here on your periodic table, you'll notice that it drops down and goes to the lanthanides, and down here it goes to the actinides, and that kind of makes sense, right? We have 6S, 4F, 5D, 6P, 7S, this would be 5F to 6D. Now, the nice thing about this is it lets us categorize where the elements are into their families just by looking at their electrons. We know that in a family group, elements have similar behaviors. Behavior is dictated by how many valence electrons you have. If you have 2 valence electrons, you're going to act like an alkaline earth metal. It doesn't matter how many electrons you have total, it's just your valence electrons. So an electron configuration lets us just look at where the electrons are. The arrangement is called the electron configuration. The lowest energy arrangement is called the ground state. All right, that's the uncharged state when the element is just in its pure form. It's not an ion, it's not a plasma, it's not interacting with anything. It's just the ground state. So ground state means normal atom. The electrons are going to stack up like this. They're going to go 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, so on and so forth. There's a pattern to it. I'll show you how to read it. So let's look at the electron configuration for each of the following. Now, this will be a whole lot easier if you can follow along on a periodic table, okay? So with carbon, the electron configuration is 1s2, 2s2, 2p2. All right, I'm going to jump back to our periodic table and we're going to walk through this. So here we go. Put myself in the middle so we can see. So 1s1 is hydrogen. 1s2 is helium. We have lithium and then beryllium. I think we have boron next. Yep, and then carbon. Okay, so let's see if we can figure this out. We said a moment ago that carbon's electron configuration is 1s2, 2s2, 2p2. So it's an address. I'm going to give the full shells, the full sublevels, starting with 1s, then going to 2s, then going to 3s. I'll read it left to right, top to bottom, just like a book. So, is the 1s orbital full? Yes. Hydrogen is there and helium is there. Since I'm on my way to carbon's little house, right, carbon's little tile, I've got to go 1s1, 1s2. Once I've finished with 1s, I write it down. So 1s2. That gets me to lithium. So am I passing lithium? Yep. Am I passing beryllium? Yep. Got to keep going. So now 2s is full. So I write it down. 2s2. I read it left to right. I go straight across. From beryllium is boron. I'm still in 2, right? Here's my 2. I'm still in the 2 row. But now I'm in the P block. So 2p1, passed it. 2p2. So I write 2p2. And that is the electron configuration for carbon. Read it top to bottom, left to right. All right? You don't have to say 1s1, 1s2, 2s1, 2s2. If you all you have to do is put the full notation, and that tells us we've already passed that whole thing. All right? Let's look at another one. So the next one says helium. So take a minute, see if you can figure out helium. It's pretty simple, all right? We don't even need to go back for that one. We'll just draw our little periodic table right here. So we know hydrogen's in the first block. D blocks down here. And we know helium is there on the left. So we're in the 1 row, so we know it's 1. The S block actually includes helium right there because helium's special. It's a noble gas, but it doesn't have 8 valence electrons. To be a noble gas, you want to have a full valent shell. In helium's case, the valence shell is 1s, and since 1s can only hold 2 electrons, if it has 2 electrons, it's full. So I go 1s, 2, because 1s1 is good, 1s2 is right there, and I could stop. I'm at helium. So there it is. Now let's look at magnesium. All right, we're just going to keep adding here. So we have lithium. We'll go back. That's easier if we just go back. All right, so we want to find magnesium. Magnesium is number 12. All right, let me grab my periodic table here. My coffee out of the way. Go Steelers. All right, so if we look at this from our periodic table, we have hydrogen, helium, we have lithium, beryllium. All right, we go across, we have boron, carbon, nitrogen, oxygen, fluorine, and then our first noble gas is neon. And then down here we have sodium, and then we have magnesium. All right, so magnesium is number 12. Now let's check something out. If I want to do the electron configuration for magnesium, I go, well, top to bottom, we're going to end up in 3. So I'm going to go 1s2. Yep, it's full, so write it down. 2s2. Yep, it's full. So that gets me to beryllium. Go across 2p. 1, 2p2, 2p3, 2p4, 2p5, 2p6. Yep, we're good there. 2p6. 3s1, 3s2. Now, we know that magnesium is number 12. That's its atomic number. We know that magnesium is neutral when it's an atom. We know that each one of these little exponents tells us how many electrons is in that orbital. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. The exponents should add up to the atomic number if you're doing the electron configuration for a neutral atom. So let's go back and check our work. We got 1s2, 2s2, 2p6, 3s2. There it is. All right, silicon. Silicon is number 14. So jump back over here. Let me grab my eraser. I don't know why they didn't give the eraser a shortcut. It seems kind of dumb. All right. So then we have aluminum. Oh, there we go. And then we have silicon. Silicon is number 14. Same thing. All right. From the top. 1s2, 2s2, 2p6, 3s2, 3p. Well, I'm only going to the second row of p, so 3p2. We can check our work. We know aluminum is number 14. It's a neutral atom. So 2 and 2 make 4. 4 and 6 makes 10. 10 and 2 is 12. And 2 makes 14. It means we probably did it right. So are we ended up with 3p2? Yes, we are. So this is called longhand notation. All right. And if you call something longhand, that implies there must be a shorthand. Shorthand is also called noble gas notation. All right. Longhand always starts with hydrogen, and you read it left to right, top to bottom. Shorthand starts with the closest noble gas that has a lower atomic number and proceeds from there. So let's look at magnesium and go back to our periodic table. So magnesium is right here. It's number 12. And number 12. Neon is number 10. So if I wanted to give the longhand for magnesium, we said it was 1s2, 2s2, 2p6, 3s2. In order to give shorthand, I want to start with the closest noble gas that I've already gone past, that is a lower number than magnesium. I have to put it in square brackets. Right? This is a non-negotiable kind of thing. You have to follow this format. So I say neon in brackets, and then I just pick up at neon. So I'm right here. The next thing takes me to 3s2. Now pay attention when you're doing, practice problems and test questions. Sometimes it'll say, do the longhand, in which case if you turn in the shorthand, I'm going to mark it wrong. Sometimes it'll say, do the shorthand. If you turn in the longhand, I'm going to mark it wrong. You got to know the difference between shorthand and longhand. So this is longhand notation, and this is shorthand. Right? And sometimes this is called noble gas configuration. Okay? So that's the shorthand. Let's do shorthand for aluminum before we leave. Well, I'm still going to start with neon, because neon is the only noble gas that I've passed. I'm going to say 3s2, 3p2. Now here's something that's kind of interesting about noble gas configuration or shorthand. Up here in the longhand, all right, on these guys, the exponents equal the total number of electrons in the entire atom. If you look at shorthand notation, right here, the electrons equal the number of the exponents equal the number of valence electrons that you have. So aluminum has 4 valence electrons. Something's not right here. That should be 3p1, not 2. This should be 3p1. See that? Aluminum has 3 valence electrons, not 4. Sorry, it was 4. Sorry about that. Silicon would be 3p2, and silicon down here would be 3p2. Sorry about that. All right, moving on along. So that's shorthand. Now, these rules that govern this, okay? There's the off-ball principle, the Pauli exclusionary principle, and Hund's rule. So off-ball says before you can fill up a higher energy orbital, you have to fill up all your low energies. The principal quantum numbers, the numbers 1 through 7, you have to fill up number 1 before you can go to number 2 before 3, 3 before 4, so on and so forth. Pauli tells us the electrons can't have the same 4 quantum numbers, which means if they're in the same energy level and they're in the same orbital and they're in the same magnetic orientation, they must have different spins. We'll see that in action in just a second. According to Hund's rule, all right, you have to put 1 electron in each energy level that's available before you put 2 in the same energy level. And we'll see that a little bit more. These rules go with what we call orbital notation. So we just looked at electron configuration that uses exponents. Orbital notation uses arrows. So orbital notation looks like this. I'm going to shrink a little bit there. You draw unoccupied orbitals with lines, and the orbital's name gets written underneath of it, like 1s or 2s or 2p. The orbital containing an electron gets an arrow. If it's got 2 electrons, it will get 2 arrows. Now, the arrows are the spin states. So an up arrow is +0.5. A down arrow is -0.5. And this will make more sense when we start to draw one of these out. Make sure you label the blanks. So if I wanted to do helium, I would write helium, 1s, up, down. That's how I'd read that, up, down. So I would say helium, 1s, 2. Now, on PowerPoint, I can't do this half arrow. It does this whole arrow. If we want to be really correct, don't do the whole arrow. Use a half arrow because it's up 0.5 and it's down 0.5. Okay? Let's do a couple of these. The orbital notation for carbon. So we know that carbon, right, when we look at its electron configuration, so we're going to do that first. So for carbon's electron configuration, we have 1s2, 2, 2s2, 2p2. That's its electron configuration. If I want to do its orbital notation, I say, okay, carbon, 1s orbital can hold 2 electrons, 2s can hold 2 electrons, and the p orbitals can hold 6 electrons. So I write 2p, just like that. In the 1s orbital, I have 2 electrons. They have to be spinning opposite of each other. In the 2s orbital, I have 2 electrons. They have to be spinning opposite each other. And in the p orbital, I have 2 electrons. Now, this is the way I would write that. And there's a reason for it, right? Let's go back and look at these rules. Hund's rule says orbits of equal energy. So if I look at 2p, 2p has 3 sets of orbitals. Orbitals of equal energy are occupied by 1 electron before any of the orbitals gets a second electron. So I can't do this. This is not allowed. Okay? I can't do it. That's not how we do things. Hun tells us that it has to be up, up, up. And once there are 3 in there, now I can double it, and they have to spin opposite. Okay? Let's look at a couple more of these. Helium. We know the electron configuration is 1s2, so its orbital notation would be 1s up and down. They're spinning opposite of each other. Magnesium, all right, is 1s2, 2s2, 2p6, 3s2. That's its electron configuration. So for our orbital notation, we write 1s, 1s, up, down, right? 2s because it's full, up, down. 2p, p can hold 6 electrons. All right, and now let's look at as we kind of move through this. So we talked about the magnetic spin number, right? And we said that's the orientation around the axis that the p orbital or that whatever orbital is in. So if we draw a 3-dimensional Cartesian plane here, we're going to label this the x-axis. We'll call this the y-axis. We'll call that the z-axis. You can have a p orbital in the y-axis. You can have one in the z-axis. And you can have one in the x-axis. Check this out. X, Y, Z. Those are the magnetic quantum numbers. If you ever wanted to put them on there, you're more than welcome to. In the 2p orbital, we have 6. So Hun tells us go 1, 2, 3. Now I can double them up. 4, 5, 6. Not quite done. We have 3s, which is up, down. So things I can tell about magnesium. It has 2 valence electrons because the valence electrons are in the orbital with the largest quantum number. I can tell carbon because here's the largest principal quantum number is 2. It has 1, 2, 3, 4 valence electrons. Helium, the biggest quantum number, is 1, the principal quantum number. It has 1, 2 valence electrons. Okay, let's do silicon. Silicon is 1s2, 2s2, 2p6, 3s2, 3p2. So we write silicon, 1s, 2s, 2p, 3s, and 3p. I'm going to throw the X, Y, and Z on there just to be particular. So, up, down, because it's full. 2p is full. So Hund's rule tells us go and fill up each one with 1. 3s is full, and then 3p has 2. That would be the orbital diagram for silicon. I can see it's got 3 is the largest principal quantum number, so it has 1, 2, 3, 4 valence electrons. That's orbital notation. All right. That's the end of this video. Okay, there are a few more notes in this PowerPoint on light. Those will be in the second video. Okay, so if you have questions, let me know. I'll be glad to give you a hand. All right.